it's referring to a single place of electron density. It could be a single bond, a double bond, or a triple bond. The idea is that it's one line between two atoms. And so we're going to talk about basic geometries of these things. If we have just two things, we're not going to talk about that case. We're going to start with three things. So three things in a line would be linear. Three things around a central atom is trigonal planar. Four things around a central atom, like carbon, four bonds, bonds. There's carbon with four bonds. That could be methane, CH4. You're going to have five things, and notice that they basically just orient themselves to be a certain distance apart. And then six things. So what you'll need to know about each of these is you'll need to be able to draw a molecule, so something like methane, CH4, and be able, you don't have to draw the molecule in a tetrahedral shape, but you need to be able to tell me that the molecule has a tetrahedral shape. I'm not going to ask you how many electron domains it has because you'll need to know that to figure it out anyway. You won't need to know the bond angles. So I'm not going to ask you bond angles. So you literally just need to be given something. So boron, what was the one we had last time? Was it bromide?
Yeah.
No one knows. There were some.
So boron tribromide, that's boron with three bonds, right? There were no lone pairs on boron. So we would draw it like this on our paper. Something like this, probably. How you draw it on the paper doesn't matter. You don't have to draw it perfectly straight or perfectly trigonal planar, but you need to know that that molecule actually is trigonal planar, and it's very helpful to just go ahead and draw it that way anyway. So the way we draw it on the paper is the way it actually is, because if they orient themselves as far apart from each other, it's 120 degrees apart, and it's going to be flat. So that's good. But when you get into the more complicated shapes, you draw a carbon, CH or methane.
How do you figure out the electron domains?
Electron domains is just the number of bonds in lone pairs. That has 3, that has 4.
So you have to draw the Lewis structure first, basically.
Or just know it.
Awesome.
Okay, so yeah, so that could be a question. Draw the Lewis structure, and then tell me the geometry. But there are two types of geometries, and one is really a refinement of the other. You have molecular geometry and electron pair geometry. And we're talking, these are actually all molecular geometries. It said they're also electron pair geometries. You'll see what I mean in a second. So molecular geometries, here's what you want to hear. Molecular geometries are the geometries of things without lone pairs. So none of these have lone pairs.
Right.
So you can describe them with only the molecular geometry. You can also describe them with the electron geometry. It's the same thing though, if there's no lone pairs.
So you could do the degrees, or you could do the...
This is pretty much all we're going to talk about today.
Electron geometry.
Know how to do both.
So molecular geometry is bonds. So these are E domains. So electron geometry is the geometry of a molecule with no lone pairs, or a molecule just looking at the bonds. The electronic geometry is a geometry that takes into account the lone pairs. Sometimes they're the same. So if you have a molecule with no lone pairs, they're going to be the same. So for boron tribromide, so I have 3 bonds, or I have 3 bonds plus lone pairs. I have 3 electron domains. I didn't have to count this because, well, there are none. So it's trigonal planar. And so on and so forth. So you see like things get big and complicated like this. This would be like, it's going to give you examples. This would be like sulfur hexafluoride. Sulfur with 6 bonds. This would be like phosphorus pentachloride. which we did in the last chapter. We showed the Lewis structure for that. So you literally just count the number of things around the central atom. Those things are electron domains. They're either bonds or lone pairs. So let's count the electron domains for each of these. How many electron domains are here?
3.
4.
Oh.
Right. So there are 4 electron domains here. So you're going to have a shape that's described like this. It would be kind of like,
Oh, there's 4, but there's a lone pair? I don't know. 3 bonds and a lone pair. Okay.
so in chemistry, if it's a wedge, it comes at you, and it's a dash, it goes behind. So you have 2 coming out like this and 1 going back. It makes a pyramid shape. So if I think of the shape without the electron pair, that's the molecular geometry. If I think of the shape with the electron pair, that means I think of one more thing. Now it's a different shape. It's the difference between something that looks kind of like this and something that just looks like a pyramid. So the molecular geometry is the shape without the lone pair thought of as a piece of it. And then the electron pair geometry is that. You'll see what I mean with...
That's
with
trigonal period. Pyramid, I mean. Trigonal pyramid. Right? 'Cause it's 3 and 1.
yeah, this is trigonal pyramidal, but that's that's one you haven't been told yet.
Oh.
But yeah, you're right. So how many electron domains are here?
4.
4. And then here, only on the central atom.
1, 2, 3, 4, 5.
1, 2, 3, 4, 5. Yep, 5. So it's only the central atom.
That you start with.
That's everything. You literally just count the number of things around it. So if I'm looking at this, and it's showing the geometry as best it can, I see something like this. If I'm just looking at the molecular geometry, I see that. Pretend the electrons aren't there. That would be the molecular geometry, and it's called bent. We'll go over these in a second. But that would be bent. If I look at the electron geometry, well, now I have more things. That's 5 things around it. So now I'd use this, trigonal bipyramidal. So depending on the number of things you count depends on whether you're counting just bonds or bonds and lone pairs.
How about something like sulfuric acid that has the 4 oxygens off of it, but then has hydrogens off of the...
You only think of the central atom. So
Okay.
sulfur has 4 things on it.
Yeah.
4.
Okay.
Tetrahedral.
But then you go to the non-bonding.
Actually, it's got 6, right?
No,
Sulfur?
No. Well, so the double bond counts as 1 domain.
Okay.
So we kind of talked about that. And in this chapter, we actually make the distinction. But if you have a double bond, it's between 2 atoms, right?
Yes.
So it's 1 bond made of multiple bonds. You can call it a multiple bond, or say there are multiple bonds, but it's one overall thing that combines the 2.
Okay.
So that's what we're talking about when we talk about domain. We're gonna take our time with this and just stop wherever we stop. I know I kind of went into it fast, but it's actually, I promise you, not that hard. Drawing the Lewis structure is harder. You really just have to see it, then you know it, right?
For you.
What is this? Okay, what do you guys think? So central atom in this. So
Central
first of
atom
all,
is
what is the central? Yeah, sulfur. What's the electron pair geometry for the compound? So electron pair geometry is going to count, it's going to be this chart, and it's going to be bonds plus lone pairs, and you just think of the lines around it, something like that.
So since oxygen's by itself, it would be kind of this side, right?
Yeah, so first you have to draw the Lewis structure. What does it look like? Fluorines have to be singly bonded, right?
Yeah.
What does the oxygen look like?
It's when it's, well, I guess it'd be off the S up top, right?
Yeah. So yeah, one bond. Okay. So is it a single bond or a double bond?
So, single bond. That would be.
Double?
Yeah, it's a double bond. Why is it a single and not a double?
Wait, is it a double? Is it double?
I'm sorry. Yeah, why is it a double and not a single?
Because of the, what's that, the
Because it needs
Formal
the,
charge? Yeah, exactly. Cool. I like that. You got it. Great. Yeah, so if we drew sulfur and it's got, if we drew that, that would be if it were a single bond. The formal charge of oxygen is -1. And then of sulfur, there's 5 here. It's +1. So there's a charge separation here and there's not there.
So this is 5 pentagon,
Yeah, so it's the same as this one.
right?
It's 5 things.
And then it's a pentagon. Not a bipolar.
No. We draw it flat on the paper.
Oh, that's right.
We
Okay.
can't draw the geometry, the real geometry.
Okay. So it
And this is also approximate. This isn't the same thing as every other one, but it's pretty much the same thing. So we don't get into details about this actually having more electron density than this, because obviously it does. But generally, it's going to have this shape. So you could have the double bond O up here, and the fluorines on the other ones.
So if, say you give that to us on an exam, we get it's 5, but why, how do we know to switch, not do pentagon, that it's the bipyramid?
There's no pentagon.
I mean, it says it on it says 5 pentagon. Oh, so that's not even an option, is what you're saying?
Yeah.
Just to throw you off.
Because it's like a 3D.
So a pentagon, it's a real shape. We all know it. I mean, this is a triangle, right?
Okay.
But we're not talking about things in 2 dimensions.
Right.
Those words describe shapes of 2 dimensions. These are 3-dimensional shape words. If you called this a line, I'd give it to you. That is, I don't know. But yeah, this is going to be trigonal planar, not triangle. And then you could make that a square, I guess, but it's not going to be. Because the square is 90 degrees apart, right? If I drew the lines 90 degrees apart, it would make a square. Or, sorry. If I drew the bonds like a plus sign or made a square, whatever to say, those are 90 degrees apart. It's actually not as far apart as if it were tetrahedral. Because you can bend them all away from each other a little bit. You can bend those 2 this way a little, and these 2 this way a little, and it'll give them more space. It'll get up to 109.5 degrees apart, assuming all 4 are the same. So that's really just maximizing for ultimate repulsion of those electrons in the bonds.
So basically, we need to memorize the numbers
So
of
here's
bonding
a
domains.
world. Yeah, so trigonal, planar, triangular. I never say that. I don't know where that came from. But yeah, so the idea is 3 things: trigonal. Geez, that's a weird word. Trigonal, planar, triangular. But then we start thinking about considering electrons. So when we talk about just the electrons, so all of these things, these are the overarching shapes.
okay.
These are all describing electron geometry. That's basically
molecular geometry.
no. These are electron pair
Oh.
geometry. So, but they're also molecular because they don't show lone pairs.
Yeah.
So electron pair geometry is the foundation. That's the first thing you think of. It's basically, it takes lone pairs and bonds as all electron domains. So we're about to, I can actually use,
I guess it seems like it's opposite, because if molecular geometry is only talking about the bonds and not the lone pairs, that's why.
so if we have this, then we have, what would be, I don't know, what is it? Yeah, that'll work. No, that won't work. Oxygen? No.
BRF.
Let's just use really normal things. So we'll use methane and oxygen. I don't know why I keep going. Oh, water. Okay, if we draw the Lewis structures for each of these, so carbon's in the middle with 4 hydrogens, right?
Yeah.
Water, oxygen in the middle with 2 hydrogens, and then there are 2 lone pairs, right? So if I ask for their electron geometry or electron pair geometry, you count the total domains, both bonds and lone pairs, as all the same. So this has 4 domains.
Uh-huh.
This also has 4 domains.
Okay.
So their electron geometry or electron pair geometry is both tetrahedral because they meet the requirement. It's just simply the number of electron domains.
Okay.
If I talk about the molecular geometry, I only think of the bonds. So now instead of 4 things repelling and thinking about what shape that is, I only think of 2 things repelling. And we just pretend those don't exist. So you get, let's see, get this one. So you've got 3 atoms and you have 2 lone pairs. The lone pairs cause that to bend. So what's the shape of that molecule? So what, not the electronic geometry, what's the molecular geometry? What's the shape of just this? So when we think about it normally, we think about the molecular geometry. When we draw them on the page, we draw them like this, and we think of it moving around in space like that. It's the more, I guess, immediately applicable one. So that's where you'd have a difference. So in the molecular geometry, you think about the bonding domains and the non-bonding domains. So I wouldn't really think about this one. So the electron geometry, you can literally just add up everything, get a number, and then get the answer. With these, you have to think a little bit more about what the lone pair do. The lone pair push down right here
Yeah, but how do you know that?
because electrons repel. That's the point of all of this. The lone pair and the bonds repel. So what you get is the lone pair, it's a tetrahedral shape. You can still see the tetrahedral shape from the electron geometry, right? So electron geometry, yeah, it's tetrahedral. I can see that. But the molecular geometry, okay, that's just the angles of the atoms. It's this angle. It's that shape. So that's bent. So bent describes actually 2 of them. So if you have this, or if you have, is that tin? No, sulfur. Okay. And if you have sulfur,
Which one are you doing?
it really doesn't seem right. I'm drawing this.
That's
SO2.
tin chloride.
SO2.
The example over in the molecular shape says sulfur dioxide.
Okay.
But the other, they're
Okay,
two different
thanks.
things.
I couldn't read it.
Yeah.
That doesn't make sense, why they push you.
Okay, so if you draw that, so both of these are 3 atoms. They would be linear if there weren't electrons, but the electrons push them down.
Gotcha.
This one pushes it down to a greater extent than that one, but you'd still call them both bent.
Okay.
So it's not that bad once you see a few of them. Some of them are the same, right? If you have 3 bonds, just like boron tribromide, it's still going to be the same for molecular and geometric because there are no lone pairs. It's only different if you add the lone pairs. And if you're asked to get one or the other, it's the difference between counting up all of them or just looking at the bonds. So here's one. So if we had carbon, and then we had, so we can compare things with 4 electron domains with different bonding and non-bonding. So let's just put maybe boxes. So we can look at one with 4 electron domains, but only 1 lone pair instead of 2. So if we were just to draw the Lewis structure for ammonia, we would draw that, and that'd be fine. How many electron domains are there total? 4.
4.
But the molecular geometry is just going to be the shape made by the bonds. So we're going to have those 3 bonds being pushed down. to make trigonal pyramidal, which is what you said earlier. Does everyone see that? The molecular geometry is the shape the bonds make. And that's what's really most important when we think about bonding.
So on that last slide, what's the difference in between the tetrahedron and the trigonal pyramid?
One
The
lone
lone
pair.
pair.
Okay.
So in going from tetrahedral, which is something like methane, trigonal pyramidal, ammonia, to water, you basically add a lone pair. So the atoms with the bonds, we're thinking like that for molecular geometry. You have four things. They separate as best they can. That's a tetrahedral shape. Here you have three bonds. The three bonds are shaped by that lone pair. The lone pair determines the shape of the molecule.
So your original slide wasn't a trigonal pyramid, it was trigonal,
This one?
yeah, the original one. Wasn't it trigonal planar though? Okay.
Yeah, so this is three of anything around it.
Okay.
This could be Br or boron tribromide, or it could be the tin, because the tin had a lone pair, if you remember. So in either of these cases, that's three things around it.
Okay.
So for the electron domain or electron pair geometry, you just count up all electron domains and match it to the correct geometry.
Gotcha.
For the molecular geometry, which is the actual shape of the molecule, you think about how the bonds are actually shaped. You don't think about the lone pair in terms of the shape, but you do think about it in terms of its influence on how it affects the bond angles.
Okay.
So again, if you have no lone pairs, you have one that's the same as the electronic geometry. Add a lone pair, and you have some new name for a shape, because now the shape looks like, it looks like a seesaw. It's kind of like this. They kind of turned it up a little bit, but yeah, it looks kind of like a seesaw if you flip it.
So
a
you'll
couple of
ask
times.
us, what's the molecular geometry of, say, one of these, and
Yeah.
then you'll say the the electron geometry, because they're two different numbers, right?
They're not numbers; they're
Or
names.
Names.
Yeah, and I'll give you a bank for this, like I would for the functional groups, because it's a lot. But yeah, that's basically it. And you'd have to know that for electronic geometry, there are only 5, because you don't differentiate between bonds and lone pairs. For molecular geometry, it's a bit more nuanced, because you're just looking at the atoms and the bonds between, or the angles between the bonds. They're influenced by the lone pair, but the shape you're thinking of is just from the bonds.
I think I keep flipping.
And it talks about the angles and stuff like that, which are good to know. Just telling you it maximizes the distance between. And same for this. So a side note, you don't really need to know this. I'm not going to test you explicitly, but know that if it's got 5 bonds, the angles are actually slightly different than if one of those bonds is a lone pair. The lone pair takes up more space than a bond. So just know that. So this bond angle is less than this bond angle by like a significant amount, but not for this class. It's still about 1095. So we can keep adding electrons all the way around. So things like this, you're going to start getting into more exotic molecules. I3 is what we saw earlier. That was drawn out. This. And so on and so forth. Octahedral, you could add a lone pair, and that's where we're going to stop. So those are things you'll just, you'll have to memorize it to some extent, but I will give you a table of values, and they'll be in order, as this comes, that's what your bank will look like. So if you can remember the sequence and stuff like that, that might help. Or the best way to do this is to actually be able to think about what it looks like. So if you're given BRF5, you can draw the Lewis structure for it, realize there's a lone pair, and just think about where the lone pair would go and how it would change the shape. That would be learning number 1, which is where you understand everything. For the second learning strategy, it would be just to understand the order and how they come, and you will be given the bank, so you can use that to get the answer and whatnot. But yeah. So these are very important when you think about how two molecules interact, because some things can fit together. Some things, how do you say, have similar symmetry or symmetry that match, and then others don't.
Okay, one last time. The electronic.
That'll be the last thing we talk about.
Electronic geometry is like the linear, trigonal, planar, tetra. That's the electronic.
Yeah, the
geometry.
first chart. You could for this part of the test, you can look at this and then maybe look at some molecules.
So that's electronic geometry.
Right, electronic geometry.
Okay.
Here.
And then the next part.
And then molecular geometry.
is the other
You,
ones.
you get the same names from
Okay.
before in the cases where there's no electrons, and you get new names for new shapes for cases where there are electrons. So you have trigonal planar just like you did. So there's no linear anymore. Linear is
Right.
out because we have lone pairs now. So there's trigonal planar. There's now instead of linear we have lone pair. It's bent. And then we have four domains. If it's all bonds, it's tetrahedral, just like it was for electronic. But now we add a lone pair, now it's a new shape. Because the molecular geometry doesn't consider the lone pair in the overall shape. You can see that there's the dashed lines for the electronic geometry still in this table. A fun exercise for you, I'm not going to do it, would be to make a table with both. So you could have the molecular geometry column here, and just add another column. It could be electronic geometry, and then list it there. So
That'd be cool.
this is really not that bad. It's much harder to actually draw these than it is to tell me what shape they are. So that's pretty much it. You want to go over the review really quickly? Just to, I don't know, do you have any other questions about what we talked about today? Let me just go over the review and try to calm everyone down. So that's where we're stopping. I don't know what comes after it. What slide? Oh, 14, that's not good. Go to Canvas.